All right, this would take us to problem 14. Okay, again, another problem written by a former student. All right, once again, thanks heaps, Mike. This is a physics teacher in his Miata with the license plate Sea-Dog is cruising on his way to Tijuana. Of course, that's exactly where I would head. When he approaches a curve banked at an angle of 20 degrees. I tell you, I used to drive a Miata. Anyway, given that the radius of the curve is 50 meters, the mass of the Miata is 1,100 kilograms, and the coefficient of static friction of rubber on concrete is 0.9, with what range of velocities can you take the turn without skidding? We want to solve for the slowest you can go before you would slide down the hill, and the fastest you can go before sliding uphill, up that incline, and out of the curve. Again, I'm assuming that you have already seen my solution to problem 12, where I talk about bank curves and design speed. And so I'm just going to kind of zip right into it here. Okay. Here we go. So they want to draw the free body diagram for if we're going at the minimum velocity. Okay. So that will look something like this. All right. I know, I'm supposed to draw a free body. Yeah, sure, why not? Okay, so here this thing is, it's what, like a 20-degree angle? Okay, there it is on the incline, right? Anyway, so we say, okay, range forces. I'm going to have gravitational force going straight down, junk, junk. I'm going to have a normal force going straight out of the surface. And then you say contact force. The other thing is, you say, now, am I going to have friction? You say, well, we want this thing to be barely making it around the curve. We want it to be going really slow, minimum velocity. So if it goes too slow, we imagine that it may slide downhill. And so we need a friction force to go uphill against it. So I'm going to draw in that friction force going uphill. This is for the case where we are solving for our minimum speed. Okay, so we're going too slow, slower than design conditions, right? We're right at the edge where we're about to slip downhill. So friction is helping to fight against it. Again, we know that our coordinate axes, the center of the circle is that way, straight left. And so when I split these things into components, I don't need to split. I'm going to have my axes, radial and z. We're looking along the tangential axis here. And so I don't have to split gravitational force up. It's going along the z, but I will split the normal force up into my radial and tick, 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 tick. That's supposed to end there. Yeah, what are you going to do? Anyway, whatever. This angle is going to be that angle of the incline, which we were told was 20 degrees. That's the angle here, right? All right, so this is going to be n cosine theta, hypotenuse, and the adjacent. And then this is going to be n sine theta. Okay, now that friction force also needs to get split into components. So it's going to have a part that's going straight horizontal, that's along the radial, and in the z. Theta is going to be here this time. This is going to be friction cosine theta, friction sine theta. And you say, now, see what's happening here? We need a force toward the center to make us turn, right? The faster we go, the bigger that needs to be. The slower we go, the smaller that needs to be. Turns out this is too big. And so friction has to go against it, see, to keep us at that rate, to cancel out part of this. I should have this arrow be shorter than this one probably. But the point is, this needs to cancel out part of it so that we have just enough to make us turn and not too much so that we would accelerate down the hill. That's the idea. So, and go to a smaller radius. That's the idea. Let's see. We're going to go to some of the forces in the radial axis is mass times acceleration. I'm just going to jump right to centripetal. We're also going to do a sum of the forces in the z-axis is equal to mass times acceleration in the z-axis. And yes, we know that acceleration in the z is going to be 0 because we're not accelerating up and down. Continuing on, in the radial, forces in minus forces out, we're going to have n sine theta minus that friction force cosine theta, right? equals m. And yeah, I'm just going to right away substitute in that centripetal acceleration is speed squared over the radius. There we go. Okay. In the other axis, okay. Again, we're trying to solve for what again? Oh yeah, we did the free body diagram. I'm sorry, we're trying to find that minimum velocity, the slowest you can go without slipping down in. And so we're trying to solve for this v when the static friction is at its limit and it's barely able to keep us from sliding downhill. Does that make sense? Sliding inward. So this is going to be at its max, so I'm going to be allowed to substitute mu n in. Okay, that's great. The mu we know, it's 0.9 on concrete. The n we don't know. And the mass of the car we don't. Oh, we do know it's 1,100 kilograms. Okay, so we still have an n that we don't know. We're definitely going to need the other axis is what I'm getting at here. So the other axis we're going to do up minus down, right? I have to call inward positive for radial. I'm going to choose to call upward positive for z. And so when I do this, forces up minus forces down. So going up, we have n cosine theta. And we have this component of friction. Don't forget about that guy. And then going down, we have mg. Yeah, equals 0. All right, there's my equations for my axes. Again, we're trying to find that v. We don't know n. We don't know f. Right? We know everything else. So we got n and f. And on this equation, we have n and f. We don't have v there at all. But I can use this equation for n and f perhaps to substitute in and get rid of a variable. So that's what I'm going to do. Why not solve and get rid of n? Well, you see this f has got an n built into it, right? We don't actually know f. We know the friction. So I'm going to substitute in the formula for friction, of course. What am I doing? Let's get that in there. So where it says friction, I'm going to say mu n. I can get away with that in the static case because we're at the limit. It's at its maximum when it's equal to mu Sn. So I'm going to substitute that in there. Right? Okay, going on the other side. So the point is, I'm sorry, getting back here. We're trying to find v. We know m. We know r. We know theta. We don't know n. We know mu, we know theta, we don't know n. I got an n here I don't know, and v I'm trying to find. And so I need to get an equation for n, so I'm going to use this. We're, of course, going to substitute in for friction there. I feel like I'm repeating myself, probably because I just repeated myself, right? Again, we're substituting in mu n for that static friction there. Okay, I'm just going to jump a step. I'm going to shove that mg to the other side. Okay, so what I'm going to do is I'm going to isolate the n here. So I'm going to factor it out of those two terms, right? So, I'm just going to factor the n out. So it'll be n times cosine theta plus mu sine theta. And on the other side, I've got mg. I'm going to take this bit in parentheses, divide it over, right? So I'm going to have that n is mg over cos theta plus mu sine theta. This is an expression I can substitute in where I see n in the other equation. Okay. When I do that, this is going to look like, give myself lots of room. It's going to be a long expression. mg over cos theta plus mu sine theta. I know what you're thinking. You're thinking, you know, this is the same expression we saw in a previous problem. Yeah, I know, because it's the same sort of situation. It's a bent curve for something going too slowly for the curve. Well, maybe it's not quite the same because there's a sign difference because it's going uphill. Friction goes uphill instead of downhill. Okay, then I'm going to do minus, right? And I've got that, really, do I really want to do that? That mu. And now I'm going to substitute in this expression for n. Hey, this is maybe a good time to point out how important it is that you can make your mu's look different than your m's and your n's. Okay? It's important so that when this is being scored, the person who is the AP grader can give you the points that you deserve. Okay? You know what I'm saying? So it's important that you make your mu's and your m's look different. Okay? Take a minute out sometime to just practice drawing a good mu, for heaven's sakes. You're like, I'm going to draw a lowercase u, right? And I'm going to draw a line down that goes down below. Make that extend nice and below. That's a little far, but you know what I'm saying? You got to make it look different than your m, okay? You want to get the points you deserve, okay? That you can show what you know. It's important, okay? Alrighty, moving onward. So this was mu times the normal force, right? And then I got a cosine theta still hanging out there. And on the other side of the equation, I've got still that equals mv squared over r. All right. Whew, we are close to the end. Okay, hey, you notice that in every term there's a mass? So I can divide through by m. Bam, bam, bam. Okay. Okay. I don't have a g in every term. There's no g in this term. Do you see what I'm saying? Okay, so I can't cancel that out. Okay, but these do have the same common denominator. I can make it look pretty. And what am I trying to find here? I'm trying to find v. This is because this is at the maximum static. It became maximum when I substituted mu n. This is the minimum speed. Okay, which is what we're trying to find. I'm going to go ahead, tidy this up. It'll be g sine theta minus mu g cosine theta all over this common denominator on the left side. Cosine theta plus mu sine theta. Now, I'm going to go ahead and move the r over, so I'm going to multiply by r, and then I want to find v, so I'm going to take a square root of this whole side, including that r. There we go. That is the setup. That is my answer. This is going to be that minimum speed I'm trying to find because I'm at the maximum static friction, barely holding it in, holding it from sliding down. Okay, so I'm going to plug in my values and solve. Okay, and this is where something, and you can decide for yourself whether you find this tragic or not. But when I punch the numbers in my calculator, because I know g, 9.8, I know theta, 20 degrees, I know mu, 0.9, I know g, 9.8, I know theta, 20 degrees, I know 20 degrees, 0.9, 20 degrees, punch in radius of 50 meters, punch in my calculator, I'll end up trying to take the square root of a negative value. This term here ends up being bigger than this term here. And so you're like, what is it trying to tell you? Okay, do you need to see that punched in? Prove that you get a negative here? Here. That numerator here is going to be 9.8 times the sine of 20, right? Look, 3.35 minus, well here, actually here, let's do that. And then I'm going to be subtracting from it mu, 0.9 times 9.8 times the cosine of 20. Like, hey, what's that? 8.2. You see that? 8.3. I'm going to be subtracting from 3.4. I'm going to subtract 8.3. That's going to give me a negative. You're like, uh-oh. And this denominator, these are all positive, right? Everything else here is positive. So you're like, so I'm going to get a square root of a negative. So you're like, oh, there is no answer. What does that mean? There's so much friction here, right? It's so frictiony. 0.9 is the coefficient. There is no minimum speed. When I put this thing down on the asphalt, it is not going to slide downhill, because that friction is so much that at this angle, it's not going to be able to slip down the hill. So there is no minimum speed. It could sit still and it wouldn't slide down. That's what that's trying to tell you. Okay? All right, so that's kind of interesting. Okay, something you might not expect could happen unless you really thought about it. But yeah, it turns out there is no minimum speed. Okay, it can go 0. All right, now it wants to know, okay, hey, what's the free body diagram? What if I'm going at maximum speed to go around the curve? You say, hey, this is going to be not so bad. This will be pretty quickly now that we've done this. Would you be upset if I just cheated and used our work here? And what I'm going to do is I'm going to say, hey, what if we're going too fast for the curve? If we're going too fast for the curve, we're going to tend to go out of the circle, right? So if this is like the top-down view of that curve, here's our Miata going along like this. You say if I am going too fast, I would tend to fly out of the curve like this, wouldn't I? I'm going to end up going up the surface, right, and going off the edge of the curve that way. So friction is going to go not uphill, but downhill to oppose the slide. So this force friction would be gone if I'm going too fast for the curve. Instead, friction would be going this way. Okay. Okay, and this is that static friction, right? Because I'm not sliding. Supposedly, if I'm going to make this curve, I'm not going to be sliding yet. It's going to be static friction. The wheels come in and out of contact. We're not skidding. And so you say, hey, what's this? This side's adjacent to theta. This would be that force of friction times the cosine of theta, and this side would be friction sine theta. And so now, look, the vertical part, f sine theta, horizontal, f cosine, it's going to be exactly the same, except it's going in instead of out and down instead of up. So I'm just going to flip the sign on the direction that friction component is going. So this will be positive here, which will track down, right? And this here is going to be negative in that axis, right? And that negative sign is going to track through here. Now when I substitute this over, in for n there and there, remember this was flipped to be positive, right? But now I'm going to have a negative. That's me cosine theta minus mu sine theta. This will be a minus, and this will be a minus, right? And so my final answer, this will be now a plus, and this will be a minus in the denominator. And so that's what it's going to look like. Let's go ahead and substitute our values in. All right, now we're solving for the max speed. All right, so coming to this side and doing the max calculation. Okay, I'm going to put my values in, if you don't mind. Here, you say it's going to be 9.8 times the sine of 20. All right, that's really sloppy. Good thing you know what it says. Okay, plus 0.9, that's my mu, times 9.8 times the cosine of 20. I'm going to divide that by cosine of 20 minus 0.9 sine of 20. And don't forget that radius is under the radical, okay? It's all this is under the radical. And that radius I'm multiplying by is, radius is turn, is it 50 meters? It is. Okay, so this times a 50, okay? All right. Whew. Plug it in the calculator. Here we go. Okay, so I'll have 9.8 times the sine of 20, okay, minus 0.9 times 9.8 times the cosine of 20, right? Yep, okay. Now notice that's giving me a negative for that numerator. That's okay because guess what's going to happen down here? Why am I getting a negative? I subtracted, I'm supposed to be adding. See, that's not going to be okay. Sorry about that. 9.8 times, oh my gosh, sine of 20 plus 0.9 times 9.8 times the cosine of 20. There we go. I get a positive value. I'm going to divide by that quantity, cosine of 20 minus, in the denominator, 0.9 times the sine of 20. Okay, that's so much better. Okay. I'm going to close parens. Okay, that's this part. Now I've got to multiply by 50 by the radius. Okay, now take a square root. Why not? There we go. 30.35 meters per second. That is our maximum speed now that we can whip around that curve at. So Vmax is 30.35 meters per second. Ta-da!